Welcome back, and we're getting started with the second tutorial session here. There is a soft copy of this problem sheet on the website, and if I'm not mistaken, it's a slightly longer sheet because it has the definition of the plurality with runoff rule, which is a part of one of the questions. The version that we printed out was a slightly older version, which doesn't have this definition. So what we'll do is, if we have time at the end, then maybe we'll just give you a brief explanation that will help you navigate that question. And also, I'm estimating that we'll still have some time left at the end. So the last question in the problem sheet is closely related to what we are going to look at now. So in the morning, what we discussed was manipulating Borda and in fact any scoring rule with a single manipulator in the unweighted setting, right? And we said that there's this natural greedy strategy that works where you look at a position and well, of course, you place your favorite candidate on top, and thereafter you basically try and place candidates based on whether it's safe to place a candidate at that position, because as you go further down, it becomes less and less risky to place candidates, just intuitively speaking. The higher up you are, the more potent it is to place somebody at a high position because you're giving them a lot of points. So you want to make sure that doing that doesn't unsettle your favorite candidate. And if by staring at the list of candidates and the scores that they have from the truthful voters, you determine that there is no candidate that is safe to place at a particular position, then you basically give up and you get stuck, and you can essentially say with confidence that there is no way that a single manipulative vote can turn the tide for your favorite candidate, right? And that requires a bit of a proof, but it's not terribly complicated. You can actually argue that this algorithm always produces the right answer. Now, the fifth question in the problem sheet encourages you to think about why doesn't this strategy work when you have two manipulators. Okay, so when you have two manipulators, you could do the same. Both of them could independently follow the greedy strategy and come up with their votes. And well, what we are going to argue now is that the problem of manipulating Borda with two manipulators is NP hard, and the greedy strategy is eminently polynomial time. And therefore, I would lean towards the possibility that you guys should be able to come up with a counterexample for the greedy algorithm, okay? Because I do believe in this argument that I'm going to present. There are two papers, as we discussed in the morning, in 2011 that established this. I think I'm following the proof given in the AAAI paper. The HCHI paper has a proof that's slightly more elaborate because it tries to achieve even more. It tries to show you that this problem is NP hard even in the setting where you have two manipulators and only three non-manipulators. So they go through a fair amount of stunts to get the number of non-manipulators also down to a constant. We're going to look at the simpler, well, not I presumably simpler version where we don't care about the number of non-manipulators, but we do show that the problem is hard with two manipulators. Yeah? Okay. All right. So I think of this as one of those examples of a hardness proof where the key is really in finding the problem to reduce from somehow. So as we discussed earlier today, this was a problem that was glaringly open for a long time, and sometimes when you have these problems whose complexity is a long-standing open problem, when the proof does come around, it ends up being a fairly intricate reduction spanning several pages, so you can't keep track of what's going on, and the gadgetry is complicated and so forth. That's often the case, but you'll find that in this case, this is essentially a two-paragraph proof, and it falls in place once you have the right problem to reduce from. So I'd say that this is one of those examples where the reduction itself it's certainly clever and cute, but it's not complicated. The key is really in starting with the right problem. So at least that's how I see it. So let's introduce the main protagonist for this part of the show. We have the permutation sum problem, and the hardness of this problem is, as far as I remember, a fairly intricate proof. So we won't be going there. I think was in a paper by, okay, I forget all the names, but I think there's a Lenstra somewhere in there, and that's a 2004 paper. So let me just describe the problem. I'm going to call it permutation sum. So you're given n numbers, which are all between 1 and 2n. I think you can assume that they're distinct, but really all I'm going to use is the fact that they add up to n into n plus 1, okay? And the question is, are there two permutations of 1 to n, okay, which are such that for all I, pi of I plus sigma of I equals xi, okay? So the ith number here can be obtained as a sum of the ith numbers in your two permutations. Yeah, that's the problem. So is the question clear? Yeah, okay, cool. All right, so so on the way to our reduction, we're just going to see a useful technical lemma, which is similar to what we saw for when we were discussing, I think, Copeland and Maxman yesterday. And we said that if you give me a graph which has certain weights, then I can give you an election for which the pairwise election graph looks exactly like the graph that you've given me, right? If you give me a directed graph with weights on the edges. So essentially, you're saying the format of the statement is that you give me a template for what you want the election to look like, and I'm going to give you votes and candidates that exactly fit that template, right? So this is in similar spirit, but more in the context of scoring type rules rather than pairwise comparisons. So what we are given here is m numbers, which are target scores that we want for our candidates, and the claim is that you can come up with an election which has, so you give me these m numbers, I will give you an election with m plus 1 candidates, which is such that, okay, and a certain number of voters, which I won't get into how many voters there are, but it's bounded polynomially, so it's not a huge instance, okay? So I can give you an election which is such that the ith candidate, so among the first m candidates, we effectively get these scores, but all of them are kind of nudged by an additive factor of c, and this is a common factor, okay? So the score of ci is si plus c, and the score of the m plus 1th candidate is y, where y is guaranteed to be smaller than c. So we need this the m plus 1th candidate, think of him as a dummy candidate that we use to basically push the scores of the other people around, yeah? And the dummy candidate is guaranteed to have a very low score, right? So essentially, among the first m plus 1 candidates, you effectively achieve these scores, relatively speaking, okay? It's just that they're all pushed up by an additional factor of c, yeah? So pictorially, this is what this would look like. So if you plot a histogram of the scores, right? So this is the cutoff at C, and the last guy has a score that's strictly below C. And if you just draw your, think of this as the C level, and you look at everyone going up from there, that's essentially the set of scores that you gave me. Yeah. Okay, so I don't want to get into the details of how you can achieve this, but this being a tutorial session, what we can do is try and work it out once I'm done, but I will give you the sort of the main tool that you can use when you try to establish this formally. So again, similar to what we did when we were trying to achieve or realize a pairwise election graph, where we introduced a pair of votes where so what happened was that for most candidates, the effect of these two votes essentially canceled each other out, but there was a bit of an asymmetry that you could use to push one particular candidate up or one particular pair up, right? So this is in similar spirit. So I have these two votes here. I hope the shape of the votes is clear. In the first one, we have the first candidate. So what am I going to achieve here? What I'm going to achieve here is that, so suppose you've constructed an election so far, and the scores so far or something, I don't care what, but let's say there's something. What happens after you add these two votes is that for all candidates except for the first one and the last one, their scores increase by m. The first candidate, his score increases by m plus 1, and the last candidate, his score increases by m minus 1, okay? So what you effectively have is that everybody's score more or less increased by m, except that for the first candidate, it was 1 less than m. Sorry, for the first candidate, it was 1 more than m, and for the last candidate, it was 1 less than m, okay? So essentially, you have managed to effect a differential for the first candidate, right? So the first candidate managed to get ahead, and the last candidate is somebody you need to sort of create this asymmetry, and that's the candidate that's going to have at the very end of this process a score of y which is less than c, right? So effectively this is, think of this as a black box process that pushes, that gets one candidate ahead of the rest by a relative difference of 1. And then you can, so what I want you to think about is how do you take this and repeat this process to achieve what we promised in the original statement, which was that you can achieve this sort of a histogram. It's not very hard once you have this module, okay? And just to make sure that we are on the same page with respect to what has happened here, let me just clarify by staring at these candidates. So remember that we are dealing with Boda throughout this lecture, right? And as I think it was pointed out yesterday, that an easy way to think about the Boda score is to just count the number of people who are ranked below you, right? So for the first candidate, the Boda score that he gets from the top is m, and from the bottom, from the second vote, is 1, right? So the additional Boda score that he receives is m plus 1. Yes? Okay. For the last guy, m plus 1, notice that he gets no points from the second voter. Okay, and he gets, so there are m plus 1 candidates in total, so he gets m minus 1 from the first voter. Yes, so his score has gone up by m minus 1. For anyone else, so let's grab the second guy. So for candidate number 2, the score that he receives from the first vote is, let's see, so it's m plus 1 minus 3 essentially, and here it is 2, right? So from the second vote he receives a score of 2, and here it's m plus 1 minus 3, right? And that's going to work out, of course, to m, but just to be explicit that this works for any of the other candidates, say that what I did for 2 will in fact work for any I, right? So if you take any candidate I between 2 and m, right, the score that they receive from the first vote is going to be m plus 1 minus I minus 1, and the score they receive from the second vote is going to be I, because they're just I positions from the bottom. Yes, this is clear? Okay, cool. So, so essentially, the I and minus I cancel out, the 1 and minus 1 cancel out, so you're left with a score increase of m, okay? So this is what has happened when you add these two votes. The first voter's Boda score increases by m plus 1. For all other candidates, their score, except for the last one, their score increases by m, and for the last one, their score increases by m minus 1. So you can sort of create this sort of a differential by using these two votes, and by repeating this process, you can create whatever shape you want, yeah, with a common offset of c. So what's your c going to be? Your c is essentially going to be m times the number of times you apply this process, right? Because that's the common extra score that everyone is getting. Question? Mm-hmm. Yeah. Okay, that's a good question. For now, let me just say that yeah. So as of now, I think the way I've described it, it may actually only be polynomial in the sum of SIs, but let's, because you're adding essentially m votes to get an additional score. Yeah, that's right. Yeah. This particular construction is polynomial in the SIs, and let's just stick to that for now. I'm not sure about doing so. So of course you could do more optimized constructions which I haven't described here, but I think for the purposes of this NP hardness proof, since we have numbers whose magnitude is polynomially bounded, we should be fine. Yeah, so even this is enough. The fact that this is polynomial in the magnitude of the SI. So let capital S be the sum of the SIs. It's polynomial in S. Yeah, so that's a good point. So I'd of course invite you to think about more efficient constructions, but I don't know if you can get it down to the log of S, but that's worth thinking about. Yeah, cool. All right. But is what's going on in the construction more or less clear? Yeah, okay, cool. All right. So now we come to the actual reduction, and I think one thing I've forgotten to mention here is whom do we want as the final winner. So I'll come to that in a second, or remind me if I forget. But this is the instance of permutation sum, and you remember what the problem is. So you're given these numbers, and you want permutations of 1 to n, so that pi I plus sigma I equals xi. Okay, so that's the instance of permutation sum. For the border manipulation instance, I'm actually going to create n plus 3 candidates. Okay, I'm going to label them C0, C1 through Cn, Cn plus 1 and Cn plus 2. I think there may be a slight deviation in notation from what's used in the paper. I think these guys use C1 through Cn plus 3. But I just wanted to keep the association between the xi's and the ci's consistent. So it's a minor thing. Okay, and here is the, so I'm going to use the construction from before to ensure that these candidates have these final scores, which are somewhat based on the xi's. Okay, so so C is the constant that we have from the previous tool. Okay, so the score of C0 is at that baseline, it's C. Cn plus 2 is the dummy candidate that we get from that construction. Okay, so his score is something strictly less than C. Okay. For any of the CIs for I between 1 and n, their score looks like 2 times n plus 2, which may not be very meaningful at the moment, but we'll come back to it. So 2 times n plus 2 plus C, so that's like a common factor, minus xi. Okay, and the score of Cn plus 1 is 2 times n plus 2 plus C. So as we try and go through what makes permutation sum useful for Boda manipulating this instance, hopefully these numbers will make a little more sense. But you can basically see that this can be achieved, I mean, this set of scores are achievable based on the lemma that we had before. So, so the first step is the construction of the instance. I want to make sure that you're convinced that you can actually construct this instance. So C, think of C as the common baseline. That's the constant that you get from that construction. And the offsets that I want is that n plus 1 has an offset of 2n plus 2, and each of the CI's has an offset of 2n plus 2 minus xi, and the first C0 has an offset of 0. So one thing that you might notice right away is that Cn plus 1 is the candidate that's clearly dominating the selection at the moment, because these are their final scores, right? These are their final scores from the truthful voters, and Cn plus 1 is pretty much ahead of everyone else. Cn plus 2 is the one that's down in the dumps, and C0 is actually pretty close to Cn plus 2 down in the dumps, because everyone else is certainly ahead of C0, right? Because they have C and they have something on top of C. Yes? Cool. So who do you think is our desired winning candidate in this construction? Sorry? Cn plus 1. Cn plus 1 is already winning, so we wouldn't really have to work very hard if we had Cn plus 1. So you don't have to see the proof, but it's more or less intuitive. C0, yeah. The reason is that in some sense, okay, at least the intuitive reasoning is that Cn plus 2 seems way too much of an underdog for us to be able to pull him back up, because notice that if you have only 2 manipulators and you have n plus 3 candidates, then the maximum Boda score that you can endow upon any candidate is 2 times n plus 2, right? Because n plus 2 is the maximum Boda score that any one voter can give. So 2 times n plus 2 is the maximum that you can propel somebody by. So this chap already has no hope, right? Because he's strictly less than C. So he's never really going to compete with Cn plus 1, even if Cn plus 1 gets 0 extra score from the manipulators, right? So if anyone has hope, that's these fellows here. But we somehow intuitively associate CIs with the XIs, and we know that the way their scores change probably have to do something with permutation sum, right? So, so at least C naught being the desired candidate would be a good educated guess at this point, and that's indeed what we are going to do. We're going to say that the two manipulators can collude and make C naught a winner if and only if this permutation sum instance is a yes instance. Okay, and again, even already um, this is not very hard to it's not very hard to predict how the proof is going to go, because notice that essentially C naught can catch up with Cn plus 1 if both the manipulators put him on top and put Cn plus 1 at the bottom, right? So then Cn plus 1's final score is stuck at 2 times n plus 2 plus C, and this guy's score goes up to C plus 2 times n plus 2. So he's already a co-winner, and we're only going to worry about co-winners at the moment. But again, once we are done with this, you guys can tweak this reduction so that it also works for unique winner. Should not be very difficult. Okay, so so now these pesky fellows in the middle are the only people we have to worry about. So right now, actually, with just the truthful voters, none of them pose a danger. But the thing is that these two manipulators are obliged to place these guys somewhere. Unlike the voting equilibria section, we don't have the luxury of saying that these guys are not going to place these candidates anywhere, okay? So you have to place these candidates somewhere in your ranking. So you want to do it carefully so that none of these guys actually end up overtaking C naught, right? And so we know that C naught's final score somehow is like 2 times n plus 2 plus C. So we need to make sure that Ci gets no more than Xi additional score, okay? But that in some sense is what permutation sum is helping us do. There is some pi of I plus sigma of I that adds up to Xi. So we just need to connect that with what are the positions at which candidate Ci should be placed by the manipulators, and then we are done. Okay, so is the intuition for this setup, is the blueprint sort of clear? Cool. All right, so so let's do the forward direction, by which I mean that assume that you have a solution to permutation sum, and let's see how we can use that to construct these two manipulative votes. Yes? Okay, so suppose you have a solution to permutation sum. So I guess it's already clear that, so this notation is to say that so these are the two manipulative votes, and what I'm talking about here is the amount of score that candidate I gets from M1's vote and the amount of score that candidate I gets from M2's vote. Okay, so in particular, what I mean here is that our friend C naught must get a score of n plus 2 from M1's vote and a score of n plus 2 from M2's vote. Okay, our candidate Cn plus 1, who was the dangerous competitor, must get a score of 0 from both of these votes, and I'm going to say that Cn plus 2, who is the benign guy, can actually go ahead and get a score of n plus 1 from both of these manipulators, because that's not going to hurt at all. Okay, and notice that if I have here a permutation of 1 to n, then I can always organize the positions of the candidates so that they get that score, right? Because now notice that the top position, the second position, and the last positions are fixed, which gives scores of n plus 2, n plus 1, and 0 respectively, right? So now somebody who is placed at the third position gets a score of n. Somebody who is placed at the penultimate position from the bottom gets a score of 1. So the border scores that are kind of hanging around waiting to be given are all between 1 and n. So if I specify a permutation from 1 and n here, you can actually go back and arrange the candidates in such a way that you respect this score vector. Okay, so in particular, what I mean by putting a number pi of 1 here, so recall that sigma and pi are essentially permutations over 1 and n. So these are all numbers between 1 and n that appear exactly once. And so what I mean by placing pi 1 here is to say that place candidate 2 in such a way that his border score from M2's vote is pi of 1. Okay, which you can always do, right? And you can do that for each of these guys because this is a permutation. Yes. And now the proof is pretty much self-evident because you know that pi of 1 plus sigma of 1 is x1, and in general pi of I plus sigma of I is xi. So the Borda score of candidate Ci goes up by exactly xi, right? And that's exactly what we wanted. Yes? So none of them actually strictly defeat C naught. Yes? Cool. Okay. Now the reverse direction is in a similar spirit. Now what we want to do is basically say that you can stare at the manipulator's votes and recover a permutation, recover two permutations of 1 to n which have the desired property. And you can probably already see why this is going to be the case, but let's just go through it to be sure. So the first point is that C naught is first on the top, because if you don't put, so now, I mean, remember that we're going the other way. So we're saying that suppose we have two manipulative votes, we want to extract these two permutations. So let's just try and reason about the structure of these two manipulative votes based on everything that we already know. So the very first point is that for C naught to have any hope at all for being a co-winner, he must be placed on top by both the manipulators, right? Because he's competing with this guy Cn here. Cn plus 1, sorry, he's competing with Cn plus 1 who has the score. Cn plus 1 similarly must be placed at the bottom. There really is no option because anything else would cause C naught to lose the election. So these are kind of forced. The next claim is that all the CIs must appear sort of in this zone. Now let's just think about why. We know that the total amount of extra, so let's just think about the candidates C1 through Cn in aggregate, okay, because that's just a convenient way of looking at this. The total amount of Borda score that I can afford to bless these guys with in total is at most summation xi, yes? Because if I just look at the total amount of additional score that these guys have gotten, if that's more than summation xi, then I know that somebody by pigeonholing has overtaken our favorite guy, yes? Okay, so the total amount of Borda score we can give these guys a summation xi, which we know to be n times n plus 1. Yes? Okay, good. Now let's look at, so if you look at the entire region here between 2 and n plus 2, okay, let's actually look at the highlighted region. So the amount of Borda score that you get by placing a candidate here is n, right? And the amount of Borda score that you get by placing a candidate here is 1, correct? So, so the total amount of Borda score that's there to go around in this zone from one manipulator is the sum of the numbers 1 to n, which is, you know, is n times n plus 1 over 2. And since there are two manipulators, the total amount of score that you have to distribute is n times n plus 1, right? So suppose for the sake of contradiction, one of the CIs slips out and gets placed at a higher position, right? Then the amount of Borda score that you get from here is in fact n plus 1, right? So let's look at, so let's assume that you actually violated the claim that I'm making here and placed one of the CIs on this sort of coveted position. Then the total amount of Borda score that you assigned was n times n plus 1 minus something plus n plus 1, okay? Is that clear? So just imagine that you shift some CI out of this zone and put him here. So you lose the amount of score that you gave from this position, but you gain the amount of score that you gave from this position. So, and you gain more than you lose, right? Because all of these positions are strictly inferior. And therefore the amount of score, the total amount of Borda score that you assign to these candidates is strictly more than n times n plus 1, okay? But which also means that there must be some candidate who has received enough score to overtake C naught. Yeah, it's just a counting argument, right? Okay, so who is the candidate therefore who must come at the second position? Cn plus 2. So he's our extreme underdog, also first at the second position now. Okay, all right. And now let's just stare at where the CIs are sitting, right? And that's going to essentially lead us to our permutations, okay? So let's say that CI is sitting at these two positions. Let's look at the amount of score that they're getting. And we know that the total amount of score that we can afford to give CI is at most xi, right? So the total amount of score we can give CI is at most xi. And this is true for all I. So you have a bunch of these sort of inequalities, but you know that these inequalities must be tight because there's really no room for slack, right? Because when you add up both sides, if you want to be all formal about it, then if you just add up all of these inequalities, you know that the sums of these permutations is 2 times n plus 2. Sorry, n times n plus 2 and the summation, so that's a typo. This should have been n and n. The sum of all the xi's is n times, so it's actually 2 typos, sorry about that. So in any case, both of these sums are the same. They're both n into n plus 1, which means that these inequalities must in fact be equalities, and that gives us a solution to permutation sum. Okay? So is everyone convinced that this reduction works? Okay. And of course, if it's hard for 2 manipulators, then it's also going to be hard for any larger number of manipulators. So just think about why that's the case. But what we normally say is that it's hard even with 2 manipulators, right? So, okay, in particular, what is really trivial to say is that there is no algorithm that can solve the Borda manipulation problem with k manipulators in general for any k, because if you were able to do it for any k, then in particular you should be able to do it for k equals 2. But to get hardness for every specific k, you still need to have an explicit reduction with an extra manipulator, but that's not very hard to do if you just think about it a bit. Okay. All right, so we still have about 15 minutes in which there are a couple of things that we could do. One is talk a little bit more about the slides that were left over from the morning session, if you like, and explain the plurality with runoff so you're equipped to solve the problem set, and also think about coming up with the greedy counterexample. I think that could be the agenda for the time that we have left.
Okay, so let me talk first about that problem for plurality with runoff in the problem sheet. Right, so that has to do with the topic of tie breaking. Right, so we talked about single transferable vote and how it can deal with ties. It can break ties as it goes. Right, so at each point when it tries to eliminate a guy, it eliminates among the guys with the lowest plurality score, it eliminates the guy who is lexicographically last. Or instead, it can do this tree where in the end, so there's a lot of people who can win for some way of breaking ties, but then eventually it still has to break ties, and it can break the ties then lexicographically. So you may wonder if there's a point in doing this more complex procedure, right? If you're going to break ties lexicographically anyway, right? Is that going to give you a different result, right? So analyzing that for single transferable vote is a bit small, right? Okay, so pigeonhole. Right, so what is the total border score of all candidates in the election? Right, so let's calculate. Right, so let's look at the first. Let's look at a fixed voter. Right, so this voter. So the first guy gets m-1 point, second m-2, etc. So it's the sum of. So I'm making a mess of the whiteboard, but it's the sum of I going from 0 to m-1. Right, so this is m-1 times m over 2. Am I off by 1? Okay, so it's that, right? Okay, and we have n voters, so the total sum of border scores is n times m-1 m over 2. Right, and so we have m candidates. Right, so the average border score is n times m-1 over 2. Right, and this guy is exactly below average. So he cannot possibly be the border winner. Okay, so that's a nice fact. Because, okay, so we know that scoring rules are not Condorcet consistent. They're not guaranteed to select border winners, but at least, so they're not guaranteed to select Condorcet winners, but at least border is not guaranteed not to select Condorcet loser. So in fact, I believe it's the only scoring rule with this property or at least it's the only scoring rule that can be defined so nicely in terms of this weighted majority graph. Right, so generally weighted majority graphs and scoring rules don't mix, but border is a nice exception. Okay, so just, I thought that makes for a nice exercise. So now, so back to the sheet. So the next thing you have to do is to establish in several steps that plurality with runoff is easy to manipulate. Right, so it doesn't fit our kind of meta algorithm framework. You cannot do it step by step, but you still can do it by considering like a few relatively simple cases, and the problem sheet gives you hints how to do so. Right, so the outcome of that kind of, or the outcome of that problem would be a polynomial time algorithm for manipulating plurality with runoff. Okay, so that was that. So I can also, okay, so in the remaining 3 minutes, right, so let me talk a little bit more about voting equilibria, because I feel that we spend all of 7 minutes on voting equilibria. I think we can spend a little bit more on those. Right, okay, so let's see how it goes. Okay, so let's focus for kind of to be specific. I had the clicker, right? Okay, so let's focus on, let's first try to understand in which case we have Nash equilibria with unique winners, right? So unique winners as opposed to ties, right? So when can it be the case that there's just one guy with the top plurality score, assuming lazy voters? Okay, so we cannot have, so I claim that we cannot have the case when everyone votes for candidate X, right? So why can't we have that? Because voters are lazy, right? So what's the point, right? So there's a lot of people, why am I voting for that guy X, right? So that's not a, so that cannot be a Nash equilibrium. Okay, and by the same token, in fact, we cannot even have 2 people voting for X and everyone else staying home. Still, one person thinks, okay, so if you just want to have X selected, the other guy can do that, you don't need me. Okay, so the possibility of having a unique winner is when everyone abstains except one guy who votes for X. So when is that a Nash equilibrium? Right. Right, so it has to be the case that everyone actually likes X. Because, okay, so let's look at this guy. Right, because if he prefers someone else to X, he can change the outcome to a tie between this more preferred person and X. Right, and if that person prefers someone to X, so he can also change his vote. Right, so it has to be the case that X is the top of everyone's ballot. Right, so this is a characterization. X is a unique winner if and only if all voters rank X first. Right, so this is the only way you can have a non-tied election. Okay, so what about tied elections? So let's try to understand their structure. So suppose the outcome is a tie. So can it be something like this? So we have 2 voters voting for X, 2 voters voting for Y. So it's tie between X and Y, but someone is abstaining. Right, no, that doesn't make sense. Because if there is a tie, the abstaining voter can actually do things. Right, so he can pick someone from that tie. Right, so whoever is tied, he has his favorite person in that tie, and we assume that there are no ties in utilities. Like every individual voter actually ranks all the available candidates. So he can be the kingmaker, so of course he won't miss that opportunity. Okay, so point is, if you have a tie, everyone votes. Right, so that in particular, that means interesting things. So if you have a 3-way tie, so it means that the number of voters has to be divisible by 3. If you have a 4-way tie, number of voters has to be divisible by 4. So basically, so yeah, so if your number of voters is a prime number, so then the only tie you can have is kind of everyone voting for a distinct candidate. Okay, so what kind of, okay, so we have established that, so let's try to understand kind of what can be the shape of this tie. And this is a theorem. It's a simple characterization, but it's sort of useful to state it. So a tie really means a very delicate balance of preferences. So we can have a tie among candidates in S. So what should we have for that? Well, first, it should be the case that each candidate in S get the same number of votes, namely n over S. So for each x in S, so it should be, okay, so it should be these guys who vote for X. So in particular, they must prefer him to every other guy in that set S. Right? Because so these are the guys we expect to vote for X. If they prefer someone else from that set, right, so any one of them can change about that more preferred guy, make that more preferred guy the unique winner. Right, so they don't want to do that, so they must have X as the preferred candidate in that set. And, okay, and this is more subtle. Now, these voters who sort of vote for X, right, they should prefer a tie between all candidates in S, size of S-way tie, to any candidate they're not voting for being the unique winner. Again, because this is something that they can implement, right? Instead of having this nicely balanced tie among everyone in S, they can say, okay, I'm currently voting in X. There's a bunch of other candidates who are tied. I can change my vote to support one of that candidate. That would break the tie in favor of that other guy, right? I can make him the unique winner, right? So for a tie to be an equilibrium, it has to be the case that these guys don't want to do that, right? So they sort of prefer this many-way tie. So here is an example. So here I have 6 voters, and I have a 3-way tie, right? So my tied set is ABC, right? And note that kind of my conditions hold, right? So this guy has A as his 3-way candidate in ABC. This guy has C, right? So it's a 3-way tie where each of the guys who votes for one of the tied candidates prefers him to all other tied candidates. So what I'm not showing here is that this guy, the first guy, actually has to prefer the ABC tie to B being the unique winner, right? And the last guy over there has to prefer the BAC tie to A being the unique winner, right? So this is a property of utilities, and it's not in the picture. Okay. And so profile admits a Nash equilibrium with a tie, if and only if there exists a set S as above. Okay, so now what's your intuition? How would you go about finding this set? Okay, I probably won't surprise you if I tell you it's NP-hard, right? So it's sort of this kind of nicely balanced kind of minor, well, you can think of it as a minor kind of set of voters, so that projected on set of candidates, so that projected onto this set of candidates, voters' preferences are very finely balanced. Okay, so now if we ignore this condition and we just look at the minor with this property, then it turns out that restricted preference is kind of too painful and complicated, so one can ask the same question for a compressed version of that rule, and that's plurality with runoff. So plurality with runoff is the voting rule that is actually used in France. So I talked about it briefly yesterday, so let me talk about it in a little bit more detail. Okay, so I'll get to these slides later. Let me just talk about plurality with runoff. So the basic description of plurality with runoff is we let everyone come to the voting booths once, then we look at the candidates with the 2 highest plurality scores, we take these 2 guys and let them compete in a runoff. And in the runoff, the decision is made by majority. Okay, now if you try to be really careful about this definition, so you have to take into account the possibility of ties in the first round, right? So in the first round, so few things may happen. First, you may have several guys who all have the top score, right? Then the 2 guys you choose have to be chosen among them. Say you have, say the top score is 25, and you have 5 guys with the score of 25. So then all of your runoffs would have to be kind of among kind of pairs of these 2 5 guys. So 5 choose 2, right? And so in your kind of, okay, so now going back to 2 ways of breaking ties, kind of one way of breaking ties would be to look at these 5 guys, look at the 2 lexicographically first among them, kind of, and then let them participate in the runoff, and pick the one who win the majority vote. And again, if there's a tie among them, then pick the lexicographically first. So let me call that the eager way of breaking ties, because I break ties as soon as they appear, right? So another option would be, so I have these 5 guys, I form all the possible 5 choose 2 pairs, right? So in each pair, I select a winner, right? So a winner is, again, a majority winner if it exists, strict majority winner if it exists. If they're tied, I choose lexicographically. So for each tie, I have a winner. So for each pairwise competition, I have a winner, right? And then among those winners, I choose lexicographically, right? So this is like lazy tie breaking, right? Okay, so there are these 2 possibilities. So this is assuming that the set of guys with the highest score is a non-singleton. If it's a singleton, well then, so the other possibility I have to consider is that I have a singleton highest scorer, and then I have a bunch of guys with the second highest score, right? So then I sort of do the same. I form all possible, so in the lazy case, I form all possible pairs between the highest scorers and the guy at the second level. So I compute the outcomes of all these pairwise competitions and choose among those lexicographically. And in the eager case, I pick the lexicographically first among the guys with the second highest score, match that person with the highest scoring guy, and choose a winner among them, right? So that would be the eager version, right? So that's kind of the full description of plurality with runoff, right? So what the problem sheet asks you to do first is to, well, first understand how these 2 versions of the rule are different, right? So eager plurality with runoff and lazy plurality with runoff can actually produce different results, right? So it shouldn't be a difficult question. So if you think about it kind of I don't know, probably not more than 5-10 minutes, you should be able to come up with one. Okay, so now that we have established that these are two different voting rows, so I would like to ask you to think about manipulating plurality with runoff, right? So we can, okay, so I think there are sort of, okay, so there's also a kind of characterization question, kind of, so there's a question there that is kind of trying to characterize who can be the winner, who can be the kind of intermediate winner on the lazy plurality with runoff, right? So that involves the term Condorcet loser. So I don't think I explained that in the lecture, so let me explain it now. So remember this pairwise, okay, remember this pairwise comparisons graph, right? So we drew a graph that had voters, that had candidates as its vertices, A, B, C, D, and we had edges according to majority. Right, and we said the Condorcet winner is the vertex with the maximum out degree. Now Condorcet loser is the sink. It's the vertex that has all kind of edges coming into it. Again, Condorcet losers don't always exist, but when they do, we certainly don't want to elect them. Right? So so the characterization result you asked to prove kind of involves the concept of Condorcet loser. So this is kind of Condorcet loser. So by the way, so here's a nice exercise that is not on the sheet, but probably should have been. Okay, so it's easy to formulate now that I have this concept, so maybe let's think about that. So the claim is that border rule never selects the Condorcet loser. It may fail to select the Condorcet winner, but it never selects the Condorcet loser. Okay. Any idea how we are going to prove it? Okay, so we look at this graph. So this is the Condorcet loser, right? And we claim that Condorcet loser cannot possibly have the highest border score. So here is a hint of sorts. So the way we compute the border score, okay, so I defined it in terms of a voter, in terms of a candidate getting a certain number of points from each voter. So I can define it slightly differently. Okay, so let me look at the HCD, right? So there are voters rank C above D, and there are voters rank D above C, right? So there's VCD and VDC, right? And these VDA and VDB, right? So these are voters respectively who rank D above C, D above A, and D above A, and D above B, right? So I claim that the sum of these numbers is actually exactly the plurality, the border score of D. Right, so in a way, so the border score of D can be computed as its score from pairwise comparisons, right? So if you're summing over pairwise comparisons. Okay, so why is that? Well, so let's think about the score of D, right? So D gets some score from the first voter, some score from the second voter, some score from the third voter. So let's ask ourselves, so how many points D gets kind of from comparisons with A, right? So A can be here, right? So when A is below D, it sort of contributes 1 to the border score of D, right? So because if A was not there, D would be like one step lower, right? And here A does not contribute to the border score of D, right? So the contribution of this, or in other words, so the contribution of this voter to the border score of D is exactly the number of voters who appear below. So A contributes here, doesn't appear there, doesn't contribute here, contributes there, right? So exactly so A's contribution to the border score of D is exactly the number of times A appears below D. So this is VDA. Right? So if you look at this sort of labeled pairwise majority graph, where each edge is labeled kind of with these two numbers, I write them close to the vertex. So here I have VCD, here I have VDC, VCD plus VDC sums up to N. Right? So the sum of numbers written next to a candidate is exactly his border score. Okay, so suppose a candidate is a Condorcet loser. What can we say about all these numbers written next to him? So they are small. How small? At most less than n by 2. Right? So his border score is in fact, okay, border score is at most m minus 1 times n over 2. Okay, strictly less, because he's a strict Condorcet loser. Okay, so why that can't be the highest border score? Total will be too actually useful. Right, so this is something I alluded to in the end of my lecture, and I won't be able to show it now, but this is something that we show in the paper. If you have single peaked or single crossing preferences, you can actually efficiently find this set, this finely balanced set with these properties. Right, and it takes sort of fairly different algorithms in single peaked and single crossing case, but in both cases there is a polynomial algorithm. Right, so it gives you, okay, so assuming that your utility is such that this condition is always satisfied, which is which is an additional assumption, but you can sometimes make it, right? So then you can actually efficiently find voting equilibria. Okay, something that is viewed, okay, what is viewed about this equilibrium? What feels wrong about it? Look at the guys who vote for C. They should be voting for D really, right? Right, so it's not a very good equilibrium. They could have been equilibrium with the tight set A, B, D, right? And that would work as well, right? So A, B, D, right? This guy voting for A, this guy voting for D, A, B, D, right? Everyone voting for their top choice. That would be another Nash equilibrium, but this doesn't change the fact that what I showed you is a Nash equilibrium, right? So Nash equilibria are not unique. You can actually still have bad Nash equilibria. Even with lazy voters, you can have bad Nash equilibria, right? So one extreme option would be, so there's this long list of votes, right? And at the bottom you have two candidates, Y and Z. Half of the voters say Y above Z, half of the voters say Z above Y, right? And then you have a Nash equilibrium where half of the voters vote for Y, half of the voters vote for Z. Again, Nash equilibrium, even though they're lazy. So this is almost as bad as kind of our bad example. It's sort of marginally better because now there is a tie between two guys, right? But that we fixed by assuming lazy voters. But still we have a very similar situation when voters are lazy, but kind of we're allowing for two, but kind of there can be ties, right? So assuming lazy or truth-biased voters doesn't completely get rid of bad equilibria. So bad equilibria are still there, so we still have to think what to do about them. Yes? Okay, so let's think about what happens when they don't vote, right? So there's a tie at between Y and Z. So suppose my preferences are YZ and I decide to abstain, right? So Z wins, right? And Z is my last ranked candidate. So as bad as Y is, Z is even worse for me. So if I abstain, the outcome gets worse for me. So I'd rather not abstain, right? So they're kind of tied between two bad options, but if anyone stays home, the outcome gets even worse for them, right? So that's Nash. Okay, so yeah, so let me stop here. So I think, yeah, so now we understand a little bit more about Nash equilibria, right? And also about plurality with runoff, right? So tomorrow we have a tutorial session. So I guess I'm happy to talk about the problem sheet. And I'm also happy to talk about some problems concerning single peaked and single crossing collections, right? So I didn't distribute the sheet, but we can just talk about them. So as I will be showing them on the slides, writing them on the board. Okay, so we have a plan. Okay, thanks.